Hi there, my name is Elizabeth, and today I'm going to be talking about graph traversal. In particular, what they are, their uses, and the types of graph traversals that exist. Before I start, I think it's important to cover some background information. So, what is a graph, and what is graph traversal? A graph is an abstract data type that consists of nodes or vertices, which are objects that are being connected. In this case, the pink circles, while the connection between the nodes or vertices are called edges or links. In this case, the black lines. Graph traversal, on the other hand, refers to the process of visiting each vertex in a graph. Traversing is also sometimes called iterating over the data structure. This theory can be applied to a range of different types of graphs, which we'll be explaining later in this video. There are different types of graphs, such as directed, undirected, weighted, and unweighted, which are important to consider when choosing which type of traversal you're going to use. In a directed graph, the edges have direction, meaning the edges have arrows that connect one vertex to another. In these types of graphs, the retrieval of the last node is not possible, since the edge of these graphs can only be traversed in one direction. An undirected graph, the edges have no direction, meaning arrowless connection. There's a bidirectional connection between nodes. On weighted graphs, the length of a path is the number of edges which are traversed. In a weighted network, the length of the path is the sum of the weights of the edges which are traversed. A weight being a numerical value attached to each individual edge. It's essential that we talk about the types of traversals that exist. A graph search technique visits each node exactly once in a symmetrical fashion. There are exactly two standard graph search techniques that are widely used: depth-first search and breadth-first search. The depth-first search, or DFS algorithm, is a recursive algorithm which illustrates backtracking to ensure all nodes are visited. DFS starts at the root node. Breadth-first traversal for a graph is similar to breadth-first traversal for a tree. The only catch here is that, unlike a tree, graphs may contain cycles, so we may come to the same node again. To avoid processing a node more than once, we divide the vertices into two categories: visited and not visited. These are two types of traversals that are widely used, and of course, due to their differences, they have their own advantages and disadvantages. If we start with advantages, DFS uses less memory than BFS. Only the path from root node to the current node is needed. Another advantage is time efficient. For graphs with many nodes or edges, DFS may be faster than BFS. Now, onto breadth-first search advantages. Optimal solution. BFS is guaranteed to find the shortest path between two nodes in an unweighted graph. Completeness. BFS is complete, meaning it finds the solution if it exists. Uniform course search. BFS can be modified to search for the shortest path in a weighted graph by replacing the queue data structure with a priority queue. Obviously, where there's advantages, there's disadvantages. The disadvantages of BFS. There's space complexity. BFS can be very memory intensive, especially for large graphs of trees. It needs all the visited nodes in a queue data structure, which can take a lot of space. And it also has time complexity. BFS can be slow for graphs with large numbers of nodes or edges. FS may get stuck in a local minimum in a weighted graph. DFS may not find the shortest path between two nodes in an unweighted graph. It might find a longer path before finding the shortest path. DFS is not guaranteed to find the solution if it exists. If the graph has circles, it may loop forever. This might seem like a lot of new knowledge and might be confusing as to how it relates to real life, but this concept is actually all around. It is commonly found in search engines. An example of a program that uses graphs would be PageRank algorithms. It measures the importance of each node within a graph based on the number of incoming relations and the importance of the corresponding source nodes. Depth-first search can be used in finding a solution to a maze. It explores every path, and if there's a dead end, it backtracks till it finds the correct path that leads to the end of the maze. Another example where BFS can be used is in web crawling. Search engines like Google use web crawling to index web pages. Starting from a seed page, BF is employed to explore and discover new pages by following links at each level in a breadth-first manner. In conclusion, while graph traversing In conclusion, while graph traversing is a fundamental concept in theory, its practical application extends into our everyday lives. The significance of graph traversal becomes evident in various scenarios, such as optimizing travel routes, efficient search for information on the internet, and expediting delivery processes. I trust that this video has enhanced your understanding of graph traversal. Should you have any additional problems, please leave a comment there, and thank you.